Hello, everybody. Welcome to the second session, stream two. I think we can describe this as mostly pure mathematics in this session. Our first speaker is Toby Lam from the University of Oxford, who is going to give us a talk about showing preservation of properties under multiplication via difference of squares. Over to you, Toby.
Great. So let's begin. So the idea of this talk really is that multiplication is just two operations, which is squaring, summing, and taking scalar multiples. And we do this using the difference of squares equation. So basically, we have a squared minus b squared is equal to a plus b times a minus b. We change it a little bit, and now we get this form where we have a product is equal to the difference of two squares times 1/4. And we would first start by showing that certain analytical properties are preserved under multiplication using this identity. And hopefully this would give us a somewhat easier proof in some metric than proving it directly. And we're going to talk about algebra of limits, product rule, and showing that products of integrable functions are integrable. Then finally, we're going to generalize this kind of method using some linear algebra and talk about similar ideas in mathematics. So the basic structure is that suppose let P be the set of be the subset of some elements that have undesired properties. So for example, we can let V be the set of all functions, and we would let P be the set of all continuous functions, something like that. And the argument and what we want to show is that if X and Y has this property, then the product has this property. And when we're proving this, instead of showing that it's directly, we're going to say that, okay, first of all, we want to show that linear combinations of elements of P are in P. So if you have two elements that have a property, their sum is going to have that property as well, and scalar multiples is going to have that property as well. And generally, step one is very easy. Step two is kind of the hard bit. So we show that squares also have that property. And then finally, we use the identity to show that X times Y has that property as well. So the first example would be algebra of limits. So we want to say that if AN and BN converges, then the product converges. So again, the first step is quite easy. The second step is going to be the hard bit. And then the third step, there's some nuance in it, because not only do we want to show that AN, BN is convergent, we also want to show that its limit is going to be the product of its limit. So let's do step two first. So this really is just a standard proof. I suppose in analysis, you have seen a direct proof of this. And the idea is that if you're only proving that AN squared is convergent, you can, when you're thinking about this term, you can immediately think of difference of squares, right? You don't have to go through that kind of weird idea of thinking of adding something and then subtracting something. I don't know if you remember the analysis proofs, but I think it's actually quite easy in this sense, at least from an educational standpoint. I think it's kind of easier to see this as kind of like when you're like a year one undergraduate student, and then you go through the bounds and you end up showing that AN squared is going to be convergent to L squared, because you're kind of assuming that the limit is going to be L squared here. And then the more nuanced part is to show that AN BN actually converges to LM. And the way you do it is that you say AN plus BN squared converges to L plus M squared because of step one. And then, so you kind of actually have the same identity, and it cancels out nicely to give you LM. So that's the idea. So we're going to move on to product rule. So again, it's the same idea. But again, in step two, this time, I would say it's also kind of easier, because again, you immediately have this difference of squares. You immediately think of what you want to do, and you get the result. This time, the challenge is more on the first step, which is that you have to deduce that because this time it's not like the convergence sequences case where you can just directly substitute L into AN and M into BN. This time you actually have to go through some calculations, but even then it's actually still quite easy. You just this time you only know F plus G squared derivative of that, and then you sub it in, you sub this in. And then after some cancellation process, you end up with the derivative of F, the product rule, So this has all been kind of trivial at this point, but I think the good thing about showing the product with this way is actually in multivariable calculus, in particular the gradient. I think when I first learned this formula, it was kind of difficult to understand because the gradient is kind of like a vector, and it just wasn't clear to me why some vector output of fg is still going to be like a sum of two vectors. But if you start off with the gradient of f squared, you can kind of understand it better, right? What it's saying is that the direction of the gradient of f squared is going to be identical to that of f. And then you also want to adjust that by some scalar multiple, which is 2f. And that's kind of intuitive. And what the identity helps you is that it's saying that the intuition you have in the f squared case is directly applicable to the fg case. In fact, if you can understand the first step, you basically understand the second step in its entirety. So the intuition transfers over. And in some sense, these two statements are equivalent. So finally, I want to go through integration, which is, again, you want to prove that products of integrable functions are integrable. I think this is also a more legitimate use of this kind of idea, because, again, if you recall, proving Riemann integrability is usually very annoying and difficult to handle, especially if you have two functions. But whereas if you're just proving that a square of an integrable function is integral, I think it's easy to think about how you're going to work through those bounds and come up with a good bound. If you wanted to do this directly instead, you had to think about when is f positive or negative, when is g positive or negative, and it becomes kind of like a mess. If you know a little bit of measure theory, you can do this for measurable functions as well. In fact, it appears in the book. And so if you're interested in that, you can look at that book. So now we've kind of go through some examples. We want to generalize this. So because in some sense, it's not that rigorous to have like this kind of idea. So we want to generalize this in some way. And the first thing we're going to do is to talk about some preliminary. So we're going to define a characteristic of a field. So a field is something where you can sum elements up, and there is going to be additive inverses, and there's going to be multiplicative inverses. And the classic example is like the real numbers, the complex numbers, etc. And the characteristic is the smallest number of times you have to add 1 to get to 0. So this doesn't exist in all cases, right? For example, in the real numbers, you can keep adding ones, and you're just going to tend to infinity. It's never going to be 0. And in that case, we say that the characteristic is 0. And as another example, if you think about integers modulo a prime number, so you could think about integers mod say 2. Then if you add 1 plus 1, it's going to be 0. It's going to be the binary system, and so in that case, the characteristic is going to be 2. So now let's try to go through the process of generalizing this. So again, we have this theorem, we have this proof, and we want to combine these two into some sort of statement. So the first thing we notice is that we kind of have this idea of linear combinations, and this makes you think about vector spaces. And so in particular, step 1 is basically saying that you want to show that P is a vector subspace of V. And so the first thing you could write down is that, okay, well, let V be a vector space, let P be a subspace. Secondly, you want this product. And in general, a vector space does not have a product, and you kind of want to define some kind of multiplicative product. And this is actually called an algebra over a field. But again, you can define this using more elementary terms, which is to say, okay, well, there is a bilinear map, V cross V to V, and well, that's all well and good. And finally, we actually want to show some kind of equivalence. But we want to say the conclusion is that if you can show the squares having a property, if and only if products have an equality, have that kind of preservation of property. So that's why in this theorem, the conclusion is that those two things are the same. Finally, we want to actually be able to use step 3. We want to use this identity, and this identity relies on two things. The first is that you want to make sense of 1 over 2, and And what that means is that you want two to be invertible in the scalar field. And so what we would do is that we would say that, okay, the field has characteristic 0 or greater than 2. Secondly, you also want the bilinear map to be symmetric, because in this cancellation process, you make use of the fact that x times y plus y times x is going to be equal to 2 of x times y. And that's basically saying that x times y is equal to y times x. So that's why you want it to be symmetric as well. The proof of this really is just what we have been doing so far. In fact, we're just, it's actually it's exactly what we've been doing so far. And so I'm not going to cover too much about it. Instead, I want to kind of talk about some kind of properties of this kind of theorem. And yeah. So again, now we can think about the last 3 examples as an application of this theorem. So in AOL, we would be considering the space of sequences. The subspace would be convergent sequences. Addition would be term by term addition. Multiplication would be term by term multiplication. And I think this kind of follows naturally from what we've been doing. So let's talk about some kind of quirks of this theorem. So does the bilinear map needs to be symmetric? Well, the dumb answer is that because we use the property, so that's why we want we use the identity, and so we want it to be symmetric. But I think a more interesting thing is to think about the cross product. So in fact, this entire theorem, if you remove the symmetric condition, then the cross product can just be substituted in, right? But in that case, well, you can let V be the R3 plane, be the R3 space, so the 3D space, and you can let P be some plane in that field in the vector space. For example, you can have this kind of plane, and then V times V for any vector in that plane is actually going to be 0, right? The cross product of a vector with itself is 0, and so this is obviously true because 0 is going to be in that plane. But then this is nonsense, because if you have 2 linear independent vectors on this plane, so if you have something like this, the cross product is going to be orthogonal to that plane, and so it's absolutely not going to be in that plane. So this is nonsense if the bilinear map is not symmetric. There's also the question of whether P needs to be a subspace, and again, I think for the proof to work in its current state, you need sums to be in the plane, and you need sums to be in the subspace, and you also need scalar products, like particularly 1 over 2. And so I think you can't really go too far without. I don't think there's a much weaker condition that you can have other than P being a vector subspace. So as for why the characteristic needs to be 0 greater than 2, this really is just a technical detail. You can just think of it as 2 being invertible. And finally, you could have used the 1 over 4 formula. In fact, it's the same thing, because 2 is invertible in the field if and only if 4 is invertible in the field. But this is kind of some algebra, and I don't think it's particularly important. So finally, again, this generalization really shouldn't be the only way this idea appears. And in fact, it would be kind of good to just kind of forget about this theorem and just think about how we use this idea of multiplication being equivalent to squaring and linear combinations. So the first thing I want to talk about, okay, so this is a kind of a conclusion. The first thing I want to talk about is isometries in geometry. So a map isometry is a map that preserves distances. So if you have 2 vectors, say these 2 vectors, you're going to have this distance. So you're going to have this distance, and no matter how you map, and no matter where you map these 2 vectors, so say you map it to here, this distance is still going to be the same. So the claim, something that you can prove about isometries, is that they preserve the dot product, given that it maps the origin to its origin. And the way you can do it is, well, first of all, you can show that tu.tu is equal to u.u. And this is by letting v in here be 0. So you would get t of u minus 0 is equal to the norm of u. And so if you, again, in linear algebra, we define a norm using the dot product. And so this would give you t on u is equal to u.u. And then once again, you have this kind of idea that's like u.v is actually just a difference of squares, but this time we're dealing with the dot product, and once again you can use this to just immediately show that tu.tv is actually equal to u.v as well. in some sense, the dot product is actually is still a bilinear map, but this time you're not mapping to V, but you're kind of mapping to a scalar field instead. Finally, a kind of more legitimate application of this, I think, is in multivariable calculus. So there's this kind of very complicated identity involving the gradient of u.u. And what you can do is that you can actually deduce this just by proving this. And again, you use this identity. And I think it's kind of clear why that would be the case. If you have to deal with u.v, you have to deal with like 6 partial derivatives. It's kind of a mess. But again, if you're interested in these kind of things, you can actually look up into Levi-Civita symbols. I think they are a very good thing to learn if you're interested in calculus in general. So again, this idea also appears, more generally in the Cauchy-Schwarz inequality. The way I like to think about it is that the product is bounded by squares, and that's really what it's saying. And the Cauchy-Schwarz inequality is so good that it deserves a talk on its own. You can deduce the triangle inequality with it. You can deduce this rather abstract statement, but if you know a little bit about integration, I think it would be kind of important in that in say functional analysis or in analysis in general, you do care about whether something is bounded or not. And this is a very useful identity to show that the inner product is going to be bounded. In fact, Cauchy-Schwarz also appear in probability theory because covariance, I think, can be thought of some kind of inner product. And so you end up having this kind of nice bound as well. I might have messed up the inequality sign here, but that's not very important. So I also kind of want to talk about some identities in integration. Again, the idea is really the same. You don't really have to think about the conditions. What it's really saying is that products is going to be bounded by some sum of squares. And it's appearing here, and you can use this to deduce this, which is also saying some integral of some squares is going to be a bound for an integral of a product. And in fact, if you're interested in this kind of stuff, you would definitely encourage you to look into functional analysis, which is about some kind of vector spaces. So say polynomials, which also kind of has a limit related, which in some sense, it has some sort of topological structure. So you can think about polynomials as a vector space, and you can also think about polynomials as some kind of continuous functions. And when you think about continuity, when you think about limits, you think about topology. So that's the end of the talk. The takeaway is that facts about powers can often be translated into facts about products. I have a website and the email. So yeah, I welcome any questions. Thank you.
So thank you very much, Toby, for your talk there. It was very interesting. It was good to see how you could simplify proofs using your method. Is there any questions from the audience at all? Okay, so just a quick question for you, Toby. Is there any proofs that you're looking at which you could apply this to in the future?
So I suppose I'm kind of looking towards it's kind of, well, yeah, I'm kind of always trying to search for this kind of identity if it pops up somewhere. Mm-hmm. And I think it's just kind of a nice idea to have, like somehow you don't have to think about products. If you have some kind of nice algebraic structure, you don't really have to think about products. You can only think about squares. And I think, in fact, I think it's like James Fallon have mentioned about something like derivations, which is kind of like a more abstract definition of the derivative over some ring or module. And I think if the ring is going to be commutative, then you actually can also use this identity in a more kind of abstract setting in the case of derivations. Yeah, so that's about.
Yeah, I don't really know much about these sort of structures, but as I was telling you, they kind of look a bit like what you were talking about the other night. So yeah, really amazing stuff. I think you're onto something deep there.
Yeah, thanks.
Okay, well, thank you very much for your talk, Toby.